Every phone, laptop, and game console you own keeps a secret about its memory. Inside the chip, the CPU, the graphics, and the AI engine do not each get their own private memory. They share one single pool. It is called unified memory architecture, and it is one of the most important shifts in computing of the last decade, even though most people have never heard of it. Let us see how it works, starting from the very beginning. Start with one simple fact. A processor is incredibly fast. It can do billions of tiny calculations every second, but it cannot hold much inside itself. The real data, your photos, your game world, the numbers it is crunching, all of that lives in memory. So every moment the core reaches out, asks memory for data and waits for it to arrive. And waiting is the enemy. The closer and faster the memory sits, the less the processor has to pause. The speed of that link shapes everything. For decades, computers kept two separate piles of memory. The CPU, the brain of the machine, had its own system memory. And if you had a graphics card, the GPU carried its own private memory, called video memory or VRAM. Two processors, two separate pools, joined by a bus. The graphics chip could not simply look inside the CPU's memory. It only saw its own. Here is the problem with that design. Say the CPU has some data, and you want the graphics chip to work on it. The GPU cannot reach the CPU's memory directly, so the system copies the data, byte by byte, across the bus into video memory. Now the very same data exists in two places. That copy takes time, it burns energy, and the graphics chip just sits and waits for it. For large textures or big batches of numbers, that copy happens over and over, and it becomes a real bottleneck. Engineers call this the copy tax. So someone asked a simple question. What if we stopped copying? What if the CPU and the GPU just used the same memory, one shared pool that both of them can read and write directly? That is the whole idea behind unified memory architecture. It sounds obvious in hindsight, but making it actually work took years of careful engineering. One pool, every processor, with no more shuffling data back and forth. This becomes possible because of how modern chips are built. Instead of separate parts spread across a board, almost everything sits on one piece of silicon, called a system on a chip. The CPU, the graphics, the AI engine, and the memory controllers all live on the same slice, right beside the memory. Packing everything together this tightly also saves power and space, which is exactly what a phone or a thin laptop needs. Because they are neighbors, sharing a single pool comes naturally. Sharing memory needs one more trick. Every engine has to agree on where things live. So they all use the same map of addresses. A given address means the exact same byte, whether the CPU asks for it or the graphics chip does. Because of that shared map, one processor can simply hand another a pointer, a tiny note that says, the data you want is right here. Now watch what that lets you do. The CPU writes its data once into the shared pool. Then, instead of copying anything, it just passes the GPU a pointer. The graphics chip follows that pointer and reads the very same bytes in place. Nothing is duplicated. Remember the copy tax. Now it is 0 bytes copied. This is called zero copy, and it is a huge win for speed and for power. But sharing has a catch. If everyone reads from one pool, the speed of that memory becomes the most precious resource. We measure it in gigabytes per second, and we call it bandwidth. A modern chip might move hundreds of gigabytes every single second. Think of it like a highway. The wider you build it, the more traffic from every processor can flow at the same time. So to feed the CPU, the graphics, and the AI engine all at once, designers make that memory very wide and very fast. There is a deeper challenge too. For speed, each engine keeps its own tiny copy of recent data called a cache. But if the CPU changes a value, the graphics chip might still be holding the old one. So the hardware constantly checks and updates these copies, keeping every cache in sync. Get this wrong, and one engine reads stale data, which shows up as a glitch or a crash. This careful syncing is called coherency, and it is one of the hardest parts to get right. Unified memory is not magic. It comes with real trade-offs. Because there is only one pool, the CPU and the graphics share the same capacity. Give more to one, and there is less for the other, and they share the same bandwidth. When both of them pull hard at the same moment, they compete, and each one slows down. Usually the system software manages this balance for you, handing memory to whichever engine needs it most, but the tension is always there. You are very likely using this right now. Apple's M-series chips are built entirely on unified memory. So are the PlayStation 5 and the Xbox, which is part of why their graphics feel so fast. AMD builds it into the processors they call APUs. And nearly every phone on Earth runs a chip that shares memory this way. It is genuinely everywhere. And this is exactly why it matters so much for artificial intelligence. A large AI model can need tens of gigabytes just to hold its weights. On an older graphics card, if the model is bigger than the video memory, it simply will not fit. But with unified memory, that same model can live in one big shared pool, and the CPU, the graphics, and the AI engine can all read it together. It is the reason a laptop with enough unified memory can run a model that used to demand an expensive dedicated graphics card. There is no separate memory ceiling to slam into. So that is unified memory architecture. We went from two separate pools and a costly copy to one shared pool on a single chip. The same addresses for everyone, 0 copy handoffs, one shared bandwidth budget, and hardware that keeps every copy in sync. If you remember just one thing, let it be this. In a modern chip, memory is something to be shared, not divided. It is the quiet idea behind the fast, efficient devices you reach for every day. Thanks for watching.